Right now, as you are watching this video, somewhere in the universe, time almost stops, light cannot escape, and physics, as we know it, breaks down. If you were to fall into a black hole, to an outside observer, you would never actually be seen crossing the boundary. You would appear frozen at the edge of the event horizon. But for you, time would continue to flow. You would keep falling, silently, inevitably. So which one is real? What is seen from the outside, or what you experience yourself? Today, through the work of Nobel Prize-winning physicist Kip Thorne and his book Black Holes and Time Warps, we will explore the most extreme edges of the universe. This is not a science lesson. This is the story of how reality truly works. For centuries, humanity believed that gravity was a simple force, pulling objects across the void. Isaac Newton described it as an invisible hand, drawing the moon toward the earth, the planets around the sun. His laws worked, and they worked well. Yet, they were incomplete. In the early 20th century, a young physicist named Albert Einstein dared to imagine a radically different universe. He suggested that gravity is not a force at all. Instead, it is the result of space itself, bending and curving around massive objects. Space and time are not separate entities. Together, they form a single fabric, space-time. Imagine a vast cosmic sheet stretching endlessly in all directions. Place a small marble on this sheet, and it barely makes a dent. Place a bowling ball, and the fabric sinks, curves under its weight. Now, any smaller object rolling nearby will naturally spiral toward the larger mass. It's not being pulled. It is following the curves of space-time itself. Einstein's vision was not easy to grasp. It challenged centuries of intuition, but it explained phenomena that Newtonian physics could not. Mercury's orbit, the bending of light near the sun, the very warping of the cosmos. And within these equations, something extraordinary appeared, solutions that suggested the existence of regions where space curves infinitely, where light cannot escape. Places that would later be called black holes. Einstein himself was cautious. Such objects seem too strange, too extreme to exist in reality. Yet mathematics does not lie, and Kip Thorne would later describe these black holes not as fiction, but as an inevitable consequence of Einstein's theory. As we explore these cosmic wonders, it is essential to understand this. Black holes are not holes in space. They are regions where space-time itself has been stretched to its limits. Their existence challenges the very way we understand the universe, the way we understand reality. Stars live delicate lives, balancing the force of gravity with the pressure from nuclear fusion at their cores. For billions of years, this balance holds, keeping the star stable, shining brightly in the night sky. But eventually, every star runs out of fuel. The balance is broken, gravity takes over, and the star begins to collapse inward under its own weight. The outcome depends on the star's size. A star like our Sun will shed its outer layers, leaving behind a small, dense white dwarf. Slightly larger stars may form neutron stars, extraordinary objects where matter is packed incredibly tightly. But when a star is truly massive, the collapse does not stop. Its core continues to shrink, becoming denser and denser until nothing can prevent the formation of a black hole. At the heart of a black hole lies a boundary known as the event horizon. This is the point of no return. Nothing that crosses this line, no matter, no light, no signal, can escape. For an observer far away, an object falling toward the event horizon appears to slow down, moving more and more slowly until it seems frozen in time. But for the object itself, the journey continues normally, passing the horizon without noticing any dramatic event. Time, it seems, is relative. Beyond the event horizon, the collapse leads to a singularity, a point where density becomes theoretically infinite, and the laws of physics as we know them break down. Space and time themselves are distorted beyond comprehension. This is the ultimate frontier, the extreme edge of reality, where our conventional understanding of the universe no longer applies. Near a black hole, time behaves in ways that defy intuition. General relativity tells us that the stronger the gravitational field, the slower time passes relative to distant observers. Close to the event horizon, this effect is extreme. Seconds for a distant observer may stretch into years for someone closer to the black hole. It is a profound reminder that time is not absolute, and that our everyday experience of the universe is limited by perspective. Kip Thorne emphasizes that black holes are not simply empty voids. They are regions where space-time itself has been stretched, warped, and compressed to its limits. Their formation, while dramatic and almost inconceivable, is a natural consequence of the universe's most fundamental laws. They are the ultimate laboratories for understanding gravity, matter, and time. To witness a black hole's creation is to see the raw power of nature unleashed. A massive star, once radiant and stable, succumbs to its own weight, curling space and time inward. Around it, the cosmos warps, light bends, and reality itself seems to twist. The event horizon marks the boundary of this cosmic mystery, a line beyond which we can only imagine what truly occurs. Black holes teach us about extremes. They remind us that the universe is far stranger than we imagine, and they challenge our understanding of time, space, and the very fabric of reality. To study them is to peer into the heart of the unknown, where science meets the ultimate limits of comprehension. Time is not what it seems. Our everyday experience tells us that seconds tick at a constant rate, that minutes and hours flow evenly. But near massive objects, especially black holes, time behaves differently. Einstein's theory of general relativity revealed that gravity is more than just a force. It is the curvature of space-time itself. The stronger the gravitational field, the more space-time bends. And as space-time bends, time slows down. Imagine standing near the event horizon of a black hole. From your perspective, your own clock ticks normally. But to a distant observer, every second you experience stretches out, elongates, as if you were moving through a molasses of time. Minutes could stretch into years, seconds could stretch into centuries. The passage of time is no longer absolute. This effect, known as time dilation, is not science fiction. It is real, measurable, and confirmed through experiments. GPS satellites orbiting Earth must account for both special and general relativity. Without correction, our navigation systems would fail. The universe itself reminds us that time is relative, shaped by gravity and motion. Now imagine two identical astronauts. One stays safely far from a black hole. The other ventures close to its event horizon. When the second astronaut returns, they will have aged far less than their twin. Time has flowed differently for each of them, a tangible manifestation of Einstein's insight. Time and space are intertwined, malleable, and dependent on gravity and velocity. Near a black hole, this phenomenon is extreme. As the astronaut approaches the event horizon, the outside universe appears to speed up. Stars blaze past in fast forward. Light itself seems distorted, stretched, and redshifted. Yet for the astronaut, everything in their immediate surroundings appears normal. Reality itself has become relative. Kip Thorne emphasizes that understanding time dilation is essential to comprehending black holes and the extremes of the universe. It challenges our intuition and our sense of permanence. It teaches us that even fundamental concepts like seconds, minutes, and hours are not universal. They depend on where you are, how fast you are moving, and how intense gravity is. Time dilation is more than a scientific curiosity. It is a window into the true nature of the cosmos. It shows us that the universe is dynamic, flexible, and far stranger than our everyday experience suggests. And it is through understanding these effects that we begin to grasp the full scope of black holes, relativity, and the extraordinary fabric of space-time itself. The universe may hide shortcuts, tunnels through space-time known as wormholes. These hypothetical passages, predicted by Einstein's equations, could connect distant regions of the cosmos, potentially allowing travel across vast distances in an instant. Imagine a tunnel linking two points in space, bending the fabric of reality itself. Entering one end might deposit you light years away, or even allow for time travel. For decades, this idea existed only in the realm of science fiction, tantalizing and improbable. Yet Kip Thorne and other physicists showed that wormholes are not entirely forbidden by the laws of physics. Mathematically, they can exist. The challenge is keeping them open. Ordinary matter cannot sustain a wormhole. The intense gravitational forces would collapse it instantly. Only exotic matter with negative energy density could, in theory, stabilize the tunnel. Even if such matter existed, traversing a wormhole would remain extremely dangerous. The tidal forces near the entrance and exit could stretch and compress objects in unimaginable ways. Time itself would behave unpredictably as the rules of relativity bend and twist along the tunnel. The concept of wormholes also brings the possibility of time travel. If one mouth of the wormhole moves at near light speed or sits near a black hole, time dilation could create a situation where someone entering the tunnel emerges in the past relative to the other end. Yet Kip Thorne warns, nature may allow the mathematics, but reality imposes limits. Paradoxes and quantum effects may prevent actual time travel. Wormholes remind us that the universe is stranger than our imagination. They illustrate the mind-bending consequences of general relativity and the flexibility of space-time. While we may never travel through one, studying these possibilities expands our understanding of gravity, causality, and the ultimate structure of the cosmos. In exploring wormholes, we confront questions about space, time, and the limits of possibility. The universe challenges us to imagine beyond what we see, to probe the edges of reality, and to consider that even the most fantastic ideas may have roots in the laws of physics. For decades, black holes were purely theoretical, invisible objects predicted by Einstein's equations. Their existence was questioned, debated, and doubted. How can one prove the presence of something that emits no light, that swallows everything, including photons? Astronomers turned to indirect evidence. They observed stars orbiting invisible companions, their paths distorted by enormous unseen mass. They studied gas and dust spiraling into the darkness, heating up and emitting X-rays before vanishing beyond the event horizon. Slowly, the presence of black holes became undeniable. One of the most striking confirmations came from gravitational waves. When two black holes collide, they send ripples through space-time itself. Detectors on Earth, such as LIGO, can measure these tiny distortions, confirming not only the existence of black holes, but also the violent, dynamic events occurring across the universe. In 2019, humanity captured the first direct image of a black hole's shadow in the galaxy M87. A glowing ring of hot gas framed the dark silhouette, providing visual proof of these enigmatic objects. The image transformed black holes from mathematical curiosities into observable, tangible reality. Kip Thorne's work was crucial in predicting how matter behaves near black holes and how gravitational waves could be detected. These observations have confirmed his theories and opened a new era of astrophysics. We can now see black holes not with light escaping them, but by observing their effects on the surrounding universe. Observing black holes is more than a scientific triumph. It is a window into the extreme, the invisible, and the profound. Each discovery challenges our understanding of gravity, space-time, and reality itself. Black holes remain mysterious, yet through science we are beginning to unveil their secrets, one observation at a time. Black holes are more than cosmic curiosities. They are laboratories for the fundamental laws of nature, testing the limits of physics in ways no experiment on Earth could ever achieve. Within these extreme objects, gravity, quantum mechanics, and relativity converge, revealing gaps in our understanding and offering clues for the future. Kip Thorne has emphasized that black holes challenge us to rethink reality. They force physicists to question the nature of space and time, the behavior of matter under unimaginable conditions, and the very origin of the universe. Studying them may lead to new theories that unite general relativity with quantum mechanics, the elusive theory of everything. In the coming decades, advancements in technology and observation will allow us to probe black holes more deeply. Space-based telescopes, improved gravitational wave detectors, and high-resolution imaging will continue to unveil their secrets. Each discovery brings us closer to understanding phenomena once thought beyond reach. Black holes also inspire the human imagination. They have entered popular culture, literature, and film, sparking wonder and curiosity. Yet beyond the spectacle, they remind us of the universe's complexity and our small but significant place within it. The study of black holes is a journey into the unknown, where every answer leads to new questions. How does information behave at the edge of the event horizon? What happens at the singularity? Could black holes reveal insights about the birth of the universe or the ultimate fate of reality itself? Through research, observation, and theory, humanity continues to push the boundaries of knowledge. Black holes are not just objects in space. They are gateways to understanding the deepest truths of physics, the nature of time, and the vast, mysterious cosmos that surrounds us. As we continue this exploration, we are reminded that science is a journey of imagination guided by evidence. Black holes challenge us, inspire us, and expand our view of what is possible. They are not only the most extreme objects in the universe, they are the keys to its deepest mysteries.